Continuing on from the previous video where we're looking at regression analysis with time series data, I'll continue with the example that's in Thomas. Now once he's performed unit root tests and tested for co-integration, he then estimates some error correction models. So let's first of all estimate a second order error correction model of our production function. So here's the statement to do that. I'm using, of course, dyn$lm as we've seen before in order to handle time series. Here's the specification of the equation. So if we run that, and then we can look at the results here, which are identical to the ones in Thomas, which of course they should be. Now let's check. Let's do the diagnostic test. Let's check for autocorrelation and heteroscedasticity. Now we can do that informally by examining the residuals. Now when I looked in the previous video at the residuals in the unit root test, I used this function ACF, capital ACF, in the forecast package, which is a nice way of drawing the correlogram. In fact, in the latest version of forecast, there's a command, a function called check residuals, which is even better. This will not only draw the correlogram, it will plot the residuals and plot a histogram of the residuals with a superimposed normal distribution, so you can check for normality. It will also, if you let it, by default, carry out or calculate a lung box or a Broish-Godfrey test. I actually don't want it to do that, so I just want it to draw the graphs. So what you need to put here is the name, check residuals, then in brackets the arguments are the LM object here, and if that's all you put, you'll get the test as well, but in this case I don't want those tests, I'm going to run them separately, so I'm putting test equals false. You'll find the details of this function, of course, in the help system. So if I run this command, you get this. Of course you have to make sure that forecast is in memory, forecast package. So as you can see here, we have a nice little graphical printout with a graph of the residuals, and then the ACF function, and then this histogram here. So looking at the ACF, you can see there's no indication of any significant correlations here, so it looks as if that's okay. But let's now run the formal Broish-Godfrey test. So I'm using the BG test function again from the LM test package. On its own, of course, it runs it as first order, which is okay. Now second order, again no indication of autocorrelation here. Now you can also, in fact, if you want, calculate the Durbin-Watson statistic. This is something that's not often generally used these days for autocorrelation testing, but you can get that if you wish by running the DW test function in the LM test package. Again, that's okay. And then finally just testing for heteroscedasticity with the BP test function that we looked at in the videos on using cross-section data for regression. And again, no problems there. So it looks as if the residuals, the error term, is fine for this second order autocorrelation model. So here's so looking at the results, so given that, we can now look at the t-values and so on. Now in fact what Thomas then does is to estimate a first order ECM to see if that's satisfactory, because obviously if a first order error correction model is adequate, then it's best to use that rather than unnecessarily large ECM2. So let's run this. Now notice here that I'm using the window function. By using dyn and package and appending the dyn $ here at the front, that enables you to deal with lags and differences. As I mentioned in the previous video, LM on its own won't do that, which is why you need the DIN package. then when you use this dyn package here in conjunction with ln, the advantage is that it automatically adjusts the sample period to take account of lags and differences. Because of course when you use lags and differences you lose observations. So this will have automatically adjusted the sample period accordingly, and in fact it estimates the data from 1962 onwards, the equation. If I'm going to compare this with an ECM1, I need to make sure that they use the same sample period. If I was to run this function without specifying using this window function here, it would again automatically adjust the sample period, but because we're only using one lag here, it would run it from 61 onwards. So in order to make sure it runs it from 62 onwards to compare this over the same sample period, I need to tell it to do that. Notice how that's done. You simply use this window function, which of course we saw how to use that in the videos on time series data, which is the function that enables you to subset time series data. So now notice you simply have to put it around the dependent variable. You don't need to put it around the whole specification. So notice what I'm putting here. I'm putting window and then diff_q, which is a dependent variable, and then telling it to start in 1962. So putting this window function around the dependent variable in this way enables you to specify a particular sample period. So this is going to estimate the ECM1 over the same sample period as the ECM2 so we can compare them. So running that, here are the results. Again, identical to Thomas. Now, let's have a look at the diagnostics. So first of all, the first order autocorrelation test, that's okay. Second order. Now this in fact does seem to indicate a problem. There is some evidence here of second order autocorrelation, that the null hypothesis is rejected here, which, as Thomas says, suggests perhaps that we do need second order lags here, an ECM2 in other words. Here's the test for heteroscedasticity, that's okay. Here's the DW test, which we don't really need to look at. So there does seem to be a potential problem with the first order model. Now another way to look at this is to test whether the restrictions which are imposed in order to get from ECM2 to an ECM1 are accepted, and this is what Thomas does next. He tests the restriction that takes you from an ECM2 to an ECM1, and in fact there are 3 restrictions required. You'll have, if you want to know why, you'll need to look in Thomas's book or work through the algebra for yourself, but in order to get from this ECM2 to an ECM1 there are 3 restrictions, but they're not restrictions simply by dropping variables. So we're not testing the joint hypothesis that a subset of variables their coefficients are equal to 0. So in other words, I can't simply use the ANOVA or WALD test, a function that I used previously, to test 0 restrictions, because this ECM1 of course is not simply derived from the ECM2 by dropping variables. So what I'm going to have to do is to run this test manually. So I'm going to do an f-test of those 3 restrictions. Now the formula, the f-test formula for restrictions is this. It's the residual sum of squares of the restricted model minus the residual sum of squares of the unrestricted, divided by the number of restrictions, 3, and then that's divided by the unrestricted SSR with the degrees of freedom here, which is 9. This of course is discussed in any standard econometrics textbook. So I need to calculate these sums of squared residuals for the restricted and unrestricted model. Now the restricted model of course is the ECM1, the unrestricted is the ECM2. So here I'm going to calculate the sum of squared residuals for the restricted model. So of course I'm first of all returning the residuals with the residuals function. I'm then squaring them, and then I'm adding them up using the sum function. So that gives me the sum of the squared residuals. So that's for the restricted model ECM1. Now I can repeat it using ECM2 for the unrestricted model. I can then put those into the formula to calculate the F-stat. And the F-test here is in fact 7.65. Now is that greater than the critical value? So the restrictions are rejected. Well, we can do that by calculating the p-value, which of course is done automatically when the function, when a particular function is applied. Here, since I'm doing the test manually, I have to calculate it myself. That's easy enough done by using the pf function, which is returns values of the f distribution. Now the details of using this will be in the help system, but what you need to do here is to, the arguments will be the test statistic, which is an f-test. Then you specify the degrees of freedom in the numerator, 3, and then denominator, 9. And then to get the value in the tail that you want, put lower.tail equals false. So that gives me a p-value of 0.00759, which means the restriction is rejected. So it looks, on the basis of the fact that there's possible second order autocorrelation and that the 3 restrictions are not accepted, that the ECM1 model is inferior to the ECM2 model. So Thomas therefore then proceeds to work with the ECM2 model. So looking back at that, we can see that here we are, ECM2. We know that the diagnostic tests are okay. There's no evidence of autocorrelation or heteroscedasticity, so we can look at the t-values. And it looks as if these particular 2 variables here, the first difference of L, the labour variable, and the first lag of that, have both got very low t-values. In particular this one, the first lag of the first difference. So what Thomas then does is to drop this variable, the first lag of the first difference of L, and re-estimate the equation. So I'm going to estimate that restricted model here. So this is the same as before, same as what I had here, but you notice I've dropped this variable here. So we can estimate that. We don't need to specify the sample size here, because the fact that there are 2 lags in here will mean it will use the same sample period as previously. So running that, here's the results. Again, these are exactly as in the Thomas text. And we notice that these results, well, let's just check the diagnostics to see if they're okay. So let's do the first order autocorrelation test. Yep. Second order, that's okay. DW, it's fine. Broich-Pagan, this is, notice I'm using the studentized version here, as it's called. That's fine. So the diagnostics are okay. And again, looking at the results, they seem to be better than the ECM2 results in that more variables are significant. In fact, the only, apart from the intercept, the only one that doesn't appear to be significant at the normal significance level is the diff L. Although again, the t-value is not too bad. We can actually, of course, do a wall test on the dropping of the first difference, the first lag rather of the first difference of L, because in this case, of course, it was simply a 0 restriction. So I can do a simple wall test as I've done before, and that restriction is not rejected, so it's accepted. So it's okay to drop the first lag of the first difference of L. So this model is looking reasonable as things stand. What Thomas finally does is to test whether in fact we can restrict this model further by imposing constant returns to scale on the long run production function. Remember, of course, in a ECM model, these variables here, the second lags of Q, K and L, comprise the long run function. So in order to restrict this long run function aspect of the equation to constant returns to scale, what that does, if you work through the algebra, is mean that you have to replace these three variables by Q minus K and Q minus L. So again, you'll have to work through the algebra for yourself to see that. So what I'm going to do is to create those two variables, Q minus L here. So that creates this variable Q minus L. Here I'm subtracting this. These variables, of course, are in ln(f)dt. So I'm using the standard matrix type notation here to identify that variable and that variable. So that creates Q minus L. Now notice that if I print it out, you'll see that it remains a time series variable, which is what we want. So there's no problem there. I don't have to use ts function here. And again, if I now create Q minus L, K minus L rather, again, it retains its time series properties. It's still a TS object, so that's fine. So now I can specify this model here, but imposing constant returns to scale in the long run means that rather than having Q, K and L, the second lags of those separately, I now have the second lag of Q minus L and the second lag of K minus L. So running that, and then we can see the results. Again, you'll find if you consult the Thomas text that these are exactly the same results as he estimates, which of course they should be. We can finally do the diagnostic tests. So first order autocorrelation is fine, second order no problem there, DW is fine, heteroscedasticity no problem. So there seems to be the diagnostic tests on the error term are fine. The final thing to do, which is what Thomas does, is to do an f-test of this restriction. Again, it's not simply we're not simply testing whether a subset of the coefficients are zero here when we go from this one here, which doesn't have constant returns to scale imposed, and this one does. So I'm going to have to run it manually. Now here we're testing one restriction, one linear restriction. Of course the restriction is that the sum of the coefficients on K and L sum to 1, constant returns to scale. So I'm going to run it again manually as I did up here by finding the unrestricted sums of squares residuals and then calculating the f statistic and then finding the p-value. So if I do the same thing here to find the sums of squared residuals of these two models, calculate the f statistic, the test statistic here, which is 1.55, check the p-value of that. It's okay, so this restriction is not rejected. So in other words, it seems that imposing constant returns to scale here is okay, so it looks as if that in the long run this production function does exhibit constant returns to scale. Okay, so that completes looking at this little exercise. So this has shown you how to use time series data and how to perform various tests and so on in R.